All right, we'll get started. So these slides have been slightly edited from the version on the website, so I'll upload these after class. In particular, I got the number of the lecture wrong, but I made a few other changes to notation and so on, so it may not be exactly what you have in front of you. So assignment 1 is out. I'm sure you've all started on it. There'll be another exercise up on Friday. You should be talking to the TAs. You should be talking to me if you have problems. TAs are there to help. We're here to help. That's what we get paid for. So are there any questions before we start? Basically what we're going to do today is wrap up the search module. We're going to tie up a few loose ends. I think the last lecture was a bit rushed, unclear. So I'm going to try and redo a little bit of that, get it right this time. Well, not that it was wrong, but I don't think it was as clear as it could be. And then we'll start on constraint satisfaction next time, the constraint satisfaction module. There's one search algorithm which we won't cover today, which we will next time. That is branch and bound, depth first branch and bound, which is a very important algorithm. There's a few that we haven't covered that are in chapter 3 in the book. You should read the book. Like heuristic depth first search, for example. When you're doing depth first search, you normally just default left to right on the nodes in some arbitrary order. But if you actually order the nodes based on their H value, then you're more likely, the ones with the lower H value are more likely to get you a goal sooner. So it makes sense to use the H value to order it. That's all heuristic depth first is. And that's in the search applet as well. There's also various multiple path prunings and cycle prunings in the search algorithm and described in the book. We're going to look at them a bit today. Sometimes you don't need them because the algorithm itself will make sure that you don't encounter paths with cycles first. Other times it won't. And there's some pretty subtle things in there. We're not going to cover all the subtleties in the lecture today. But again, they're in the book and you're responsible for them. Okay, so any questions before we get started? That's where we're going. So say some clarifications, and we'll do multiple path pruning. Then we'll look again at iterative deepening and IDA star. And then we'll do a sort of overall summary of the search module, cover the search module learning goals, which will allow you to check what you're supposed to know, see if you do know it. So, just a little clarifications for the A star proof that we did. We defined two lemmas about prefixes of a solution path So we talked about lemmas about prefixes of a solution path, and I actually did call the prefix PR, which is not a good choice. Better for variables to have a single letter, so we'll call it X here. Just some clarifications in case you don't know, but I'm assuming that people know what a lemma is. It's like a mini theorem. It's not really important in its own right, but it's a stepping stone to the big proof. It's a way of modularizing the big proof. So you have smaller steps in the big proof once you prove the lemmas. And what the idea of a prefix is, I just sort of rushed over that again, but a prefix in this context, a prefix of a string is any substring that starts at the beginning of the original string, right? But we're talking about paths here. So a prefix X of a path S is a subpath starting from the same node as S, right? That's important. So if S is A, C, Z, E, D, and we'll use a shorthand notation for that, or just without the parens and the commas, A, C, Z, E, D. All prefixes of that path are A, AC, ACZ, ACZE, ACZED. And you can't use permutations, you can't start anywhere else, and so on. So the order is important in the prefixes. So if you've got your cards ready, which of the following are prefixes of AI is cool? It's a funny phrase. Should be able to just bang that out. Could be none, one, more than one. Yeah, red and green. But what's important is to notice that there's a difference between AISC and AISC, right? If you've got a repeated node, you have to repeat the node in the prefix. So that's a loop, a self loop, where a node goes back to itself, which is a cycle. And this is just a remark here. The optimal solution won't have a cycle if all path costs are greater than zero. We're going to look at that in more detail. So let's look again at this admissibility proof, and we'll deal with an example this time. Maybe that'll make it clearer. I think it was a little too abstract last time. So we have this graph. We're going to start at the node A as a start node, and D is a goal node. And the way I've drawn it implies that this is the shortest path, which is it is indeed the shortest path. So we can see what happens on that. So let's just say that F min is the cost of an optimal solution path, okay? We're saying if a solution exists, there's an optimal solution, the cheapest one. There may be more than one that's exactly the same cost, but there is at least one that has the cheapest cost. And in this case, in our example, we'll say it's ACZED, going along that path there, right? We don't know the cost of that path, but it's finite if there's a solution. So this is an optimal solution path S, and we prove, or we will prove, these lemmas for any prefix x of S. So any subpath of this path starting at A, so A or AC or ACZ or ACZE or ACZED, the whole path is a prefix of itself. These are the lemmas that we prove, which I believe, and we've emphasized this, are straightforward, and you should be able to prove them. Obviously, if this path is optimal, then for any prefix on an optimal path, the cost function f for any subpath, like for ACZ, so f of ACZ, which we sometimes just refer to as f of z, okay? Sometimes we use the node at the end of the path, sometimes we use the path itself, because the h value, the cost up to that node we know, and the h value from that node on depends only on the end node. That cost must be always less than or equal to f min, because the h value always underestimates the cost less. So h is guessing what it costs to go from z to d, and it's got to be less than or equal to the actual cost, which is the sum of the two arc costs, ZE and ED, right? So that must always be true for any prefix on an optimal path. And there's always one such x prefix on the frontier by induction. So what do we mean by that? We mean that initially, this is the only path on the frontier, the null path starting at the start node, right? And it has a cost, f of a will be less than or equal to f min. And every time you expand that, you will generate subsequent nodes, and at least one of those will be on the optimum path. And if you haven't yet reached the goal of whose f is f min, in other words, the f values you're looking at are less than f min, that will still be there. And when you expand it, there'll be another one there. So every time you have a subpath with this property on the optimal path, there'll still be one on the optimal path when you expand it, as long as you haven't expanded the goal node whose f value is f min, right? That's the induction step. So we use those lemmas to prove that A star only expands paths x with f of x less than or equal to f min. until it expands f min and says, oh, that's a goal, I will stop. I found the shortest path, right? So then you're basically done. The key points are that there are only a finite number of paths which gives us completeness, right? There's only a finite number of paths whose f value is less than or equal to f min. So you look at each of those, that finite number, eventually you get to f min and you stop. And the reason that you reach the optimal path first, which is the optimality criterion, you can show that solutions with cost greater than f min will not be expanded, okay? Because you're only looking at f values increasing up to f min when you stop, right? The way we show there's only a finite number of such paths to look at that whose f value is less than or equal to f min, we say, well, we know that no arc has value or cost less than C min, the minimum cost, right? So if there's only a certain number of arcs you can go along any path, incurring at least C min as you go along before you eventually have a path cost of greater than F min. And you'd never expand beyond that. So there's only a finite number of those because there's a finite branching factor, right? So that's where we use the minimal arc cost has to be greater than some positive number. Okay, that's what gives us only a finite number of paths. If there weren't such a lower bound, there could be an infinite number of paths, as I showed you with the Zeno example. Okay, I've really given this proof 3 times, but you know, it's important to get it straight. So hopefully I've clarified it this time. Any other questions about it? Any questions about it? All right. Hopefully that's because you're bored because you've got it the first time. Maybe you got it the second time. If not, I hope you got it this time. If you didn't, we'll talk about it. Okay, one point that I really want to stress, and I haven't stressed it enough, is, and I've talked about it, but I haven't really given a slide on it, is there's a difference between the state space graph and the search tree. Okay, the reason I haven't emphasized that is that when there are no cycles or no nodes with more than one parent, they're exactly isomorphic, one-to-one. They look identical, right? So it's very easy to confuse them because they look exactly the same. So here's an example of a tree-shaped graph, right? This is the start node. This might be the goal node, right? There's no shared substructure. There are no loops, no self-loops, no cycles. So that's the state space graph, and here's the search tree. Okay? So here's K at the root, and then there's KB, and there's KC, and KBZ, and so on. So although the graphs look identical, this is just the same graph as this one turned on its side, it's exactly the same graph, the labels on the nodes are really different. Right? So what do the labels on the node represent? Well, the nodes in this tree, in the search tree, correspond to paths. So this node here, KBZA, in the search tree corresponds to this path, KBZA. Okay? So what do these numbers here represent? This is on the search tree here. I've numbered these 1, 2, 3, 6, 7, 8. You got your cards. You only have a binary choice. You got at least 50% chance of getting it right. Hopefully you'll beat the odds. Right. It's the order in which they're expanded as they're taken off for our generic search algorithm, the order in which they're expanded, taken off the frontier. Okay? Question?
Yes, can you go back one slide?
Sure.
If there's a path from B to D, there still will be a cycle. That would
B to D?
Yes.
Yes.
Can we consider that as a tree?
Well, we're looking, in the search graph, we always start the search tree here at the root, which is a start node. Okay? So the start node here is K. We're assuming it's K. And there's only one start node in this case. There could be more, but in this case there's one. So this is the only tree we're going to generate. We're not going to generate a tree. I mean, there is a subtree based at B, if you like, here. Right? Is that what you meant?
No, I mean, if we have a path from B to D, can we still consider this graph is just like another tree?
Oh, if you just have B to D? If there's a link here, an arc here, you mean?
Yes.
Oh, okay. If you have an arc from there to there, this node has two parents. So it's a tree. It's not a strict tree. I mean, depending on how you define the notion of tree, but there are no cycles in that graph. But there's shared structure here. So in that case, I say you could still call it a tree, but it's not a strict tree where there's no common, when no node has more than one parent. Okay, so it depends on your definition of tree. And in computer science, we're a little vague as to whether it means tree or strict tree. Okay, so but in this, the search tree is always a strict tree, and there's never an arc from there to there, for example. Okay. Okay, so that's the order in which we're expanding when we number the nodes in the search tree. This is all just review. But here I've introduced cycles. So this is a bidirectional edge, so there's really one edge going this way and one edge going this way. And same here, one there and one there, right? So there's a state space graph which has got cycles in it. And here's now the search tree. Again, using breadth first search, I've showed the order of expansion of the nodes. And I've labeled the nodes according to each node has a label which is a path. So see how different this looks from this. Right? So it really is important to remember there's a difference between the search tree, which is a strict tree, and the state space graph, which might be a strict tree, a tree, or an arbitrary graph with cycles or self-loops or common structure. Okay, so if you've got your cards, then what do nodes in the search tree represent in the state space? Nodes in the search tree represent what in the state space? From 2 slides ago. Okay, most of you are getting paths, which is correct. People want me to label these things. Well, I'll label that one. What do edges in the search tree represent in the state space? What does an edge in this tree represent over here? What do you think? I mean, if these nodes are paths, and I'm going from this path to this path via this edge, what does this edge represent? It represents exactly an edge over there. Okay, so kind of a trick question, but it's still a reasonable question. Because when I go from the path KB to the path KBK, I've gone from there to there and back to there. So this edge here represents the back edge from B to K. It's the extension of the path KB to the path KBK. Okay? Okay, so the state space graph, again, may contain cycles. The search tree, nodes in this tree correspond to paths in the state space graph. You might have multiple start nodes. If I had, I don't know, C and K were both possible start nodes over here. I would have multiple trees over here with separate roots, okay, a forest, right? If there were multiple start nodes. And this cannot contain cycles or any shared structure. Okay, so what about these cycles? What do you do with cycles? We haven't talked a lot about that. Why don't we just eliminate them? Well, actually, here, for example, this path here, KB, KB, represents a cycle. It represents going from there to there, back to there, back to there, and so on. And you could say, well, that's silly because we don't want, if we're looking for shortest paths, clearly no shortest path will contain a cycle. Because if it had a cycle in it, you could just snip it out on the node where it comes back to itself, and the extra loop is redundant work, so you don't need to include that in the optimal path. That's true. But sometimes you want multiple solution paths, okay? So, we've talked about this before. Cycle checking, if you only want optimal solutions, right? If that is the case, then you can prune a node n that is on the path from the start node to n. This pruning cannot remove an optimal solution. Call that a cycle check. So here, this is the node n. If you come back to a node that's already on the path, you've hit a cycle, and you can prune that node altogether. In other words, you can prune that total path, right? And we talked about how to do that with depth first. You can do that with just a single bit on the node, which you set on the way in. And if you ever encounter that node again further down, you encounter a node with the bit set, you can fail at that point. But as you fail out of that path and try another route, you have to reset the bit to 0. So this is described in detail in the book. Any other methods, because you can get away with that in depth first, because you're really only exploring one path at a time, right? Whereas all the other methods, you might have multiple paths active, so you can't just set a bit on a node on one path, because another path might also want to use that node, and it wouldn't be a cycle, just a different path trying to use it, right? So you'd have to actually, every time you come across a node, you have to search up the path you're on and check that it isn't already on the path. Again, to distinguish between the search space and the search tree, if you have cycles or multiple parents, then obviously the search tree can explode. All right, here's a very simple example. We just have 4 nodes. And we just have 2 different ways of getting from A to B. 2 different actions from state A will lead you into state B. Similarly, from B, 2 different actions will lead you to state C, and so on. Then searching that, you would have 2 ways of getting to B, 2 ways of getting to C, and so on. So even though you have D nodes, only D nodes here, or D plus 1 states, say, the search tree has depth D, and so there are 2 to the D possible paths through the search space. So there's the exponential blow up in the size of the search tree compared to the original search space. Okay, here's one way to implement this multiple path pruning idea. And this is, multiple path pruning is more general than cycle checking. It includes cycle checking, because if you think about a cycle, shows you there are 2 ways to get to the node, the original way plus a second way when you get back to it on the cycle, right? But you can have multiple paths without cycles. So here's an example where there are 2 ways to get to n from S. You could go this way or you could go this way. And we don't know which is the best, right? And in fact, in A star, it's not always the case that the shortest path will be found first on this route. That's a subtlety that the book goes into in more detail, but it's important to know that. But if you only want one path, not necessarily the optimal path, right? Suppose you only want one path to the solution, then if you only want one path to the solution, you can prune a path to a node n that's already been reached by a previous path, right? So we're not talking about cycles here, so we can't use the cycle check. And the way to do that is to have a data structure, probably just a list, that's called closed. Say, if you look on Wikipedia for A star, you'll see closed used quite a bit. Closed, open are the set of all nodes that remain to be expanded. Closed is a set of nodes that have already been expanded. So whenever you come across a newly expanded path, then you just check when you generate a new path with n at the end of it, see if n is on the closed list. If it is, you can just ignore that new path. But again, that won't give you the optimal path necessarily, but if you're just interested in any single path to a goal node, this will work. Okay? However, what if you want optimal solutions, which you usually do? So what if a subsequent path to n is shorter than the first path to n? We want an optimal solution. Okay? And we're going to work on an example of that. So you can remove all paths from the frontier that use the longer path, right? So suppose, I don't know, I first found this path to there, has a cost of 4 to get there, right? But then later I expand this path, I get there, I find that this is 3. I might have already expanded this path beyond that node to here, and I subsequently expand this one. You might ask, why can that happen? Well, we'll see an example in a minute. If that's the case, then you should take this shorter path here and cut it in place of this longer path there, obviously, if you're interested in the optimal solution. Right? So remove all paths from the frontier that use the longer path, because they can't possibly be optimal. We know a better way of getting there, right? That's just what this says. What if the subsequent path between is shorter than the first path? Blah, blah. Change the initial segment of the paths on the frontier. Use the shorter path. Ideally, this won't happen for an algorithm. Say, unfortunately, it does sometimes, and we have to look at which algorithms where this could happen and where it can't happen. Okay, so I'm going to ask you a question. Which algorithms do you think this can't happen, where a subsequent path to a node is shorter than a path you've already discovered? Okay, so let's just consider 2 algorithms: least cost first search, or A star. Could one of those, or both of those, or none of those find a shorter path? Could it be guaranteed to always find the shortest path first, or in other words, does not ever find a shortest path after finding a longer path to a node? Okay? Okay, I'm seeing some yellow, some red, some green, some blue. Pretty well, it would be useful to have clickers here to see what the actual distribution is. So it turns out least cost search first, or least cost first search, can never find a shorter path after a longer path. Now, it's always guaranteed to find the shortest path first, because it's so conservative, right? If you think about it, it's just expanding paths in order of their total cost so far. So there's no way it could not find the shortest one first. Okay? So we know for sure that least cost search, first search, it's backwards, is guaranteed to give you the right property. And you think that A star would. Turns out it doesn't quite. Sometimes it does, and sometimes it doesn't, and we're going to look at the property when it does. But the trick with A star is that it's guaranteed to produce the least cost first solution to a goal first, but not necessarily to all intermediate nodes, depending on the heuristic function. Okay? So the proper answer is this one. It's guaranteed to always find the shortest path first. A star does under certain conditions, but often cannot. Okay, so it's certainly not both of them. Okay, so which of the following algorithms always finds the shortest path first? Only least cost first search, like Dijkstra's algorithm does. Okay. But for A star, this is only guaranteed for nodes on the optimal solution path. Okay, so let's just look at an example where A star screws up. In other words, finds a longer path first to an interior node. Okay, so there's a goal state here. This is a simple example. We've got a goal state and a start state. We're trying to get from there to there. And I put the actual arc costs on each arc. And I've got a heuristic function, which is admissible. So it's always less than the cost to go from where you are to the goal. So it's perfectly admissible, nothing wrong with that. It's a bit strange, but anyway, serves to screw up A star sufficiently that we expand the upper path first. If you actually run A star on this algorithm, I can't remember if I put this in AI space, I think not, but you could easily type it in, draw it in, check it out. But you can just run it in your head, right? So here's a start state. We expand, say, to these nodes here, right? And so the F value for this node is 2 plus 0, because it's cost so far, plus h. And for this one, it's 1 plus 10 is 11. So this is cheaper. You expand that one. You get to here. The F value for that is 5, right? So you might come back here, and you might even expand this one to get to there, to the goal state, and its F value will be now 24. This guy's waiting back here because its F value is 15. So it will be expanded next. You get to there, and its F value will be 2 plus whatever its heuristic value. It didn't put its heuristic value in there. It doesn't matter. We will eventually get to expand this to there, and so we get there having incurred a cost of 3 along this path and 4 along that path. So this path is cheaper, but we expanded the longer path first. We didn't expand the goal state first, so the conditions of the A star admissibility theorem are still holding. We're still going to find the cheapest path to go first, because we're going to use this path here plus 20, that'll get us there, 23, which is better than 24, which was the value for F coming this way. So we'll expand this path to goal before we'll expand that path to goal. So we still get the cheapest goal state first, but we didn't get here by the cheapest route first. Okay? So that's the counterexample that shows that A star is not guaranteed to find the shortest path first on interior nodes. Okay, so I just want to point this out because it's very important, and you should look at this. There is a special condition. If you put a condition on the heuristic that essentially says it satisfies the triangle inequality. So for example, if you're using Euclidean distance, as we did like in the map route finding examples, it satisfies the triangle inequality, right? In other words, you've got any triangle, the distance between any two vertices is shorter than the distance by the third vertex. Okay, that's the triangle inequality. In general, that's called the monotone restriction on the heuristic function. If you derive the heuristic function by simplifying the problem, by throwing away the constraints, the way I showed you, to exactly solve a simpler problem, and that's your heuristic value for the more complex problem, it will always satisfy the monotone property. And so there you can be guaranteed that you'll always find the shortest path first, even on the interior nodes, because it satisfies this algebraic inequality. So check that out in the book. I'm not going to go into the details in class, but you should know about it. You don't have to prove it. There is a proof in the book that actually guarantees that you'll always find the shortest path first. You're not responsible. It's a bit too esoteric. But you need to know the fact that if you put this monotone restriction on the heuristic, then A star is guaranteed to find the shortest path first. And that has wonderful consequences for the complexity of your algorithm, because you don't ever have to check now when you get to a node that you could have got there by a longer path earlier. Okay, so it really pays in many ways to use such a restriction, and there are simple ways to get it, namely use a distance metric or use a simplified problem exact solution as your heuristic, and that's usually the best kind anyway. Okay, so this is a summary on pruning. Sometimes you don't want pruning. Actually, multiple solutions may be good. You may fail, you may think this first optimal solution is going to work, but it turns out a bridge is being washed out. And you can't get along that road, so Google Maps needs to find you another route that's slightly longer. The search tree can be exponentially larger than the search space, so pruning, that means that pruning is important, because we're dealing with very large search trees sometimes. In DFS type search algorithms, you could do constant time cycle checks. BFS type search algorithms are memory heavy already, and then you can store the path to each expanded node and do multiple path pruning to get rid of extraneous paths. You don't want to multiply them unnecessarily. Okay, so that was really all just clarification in going over previous examples and theorems and lectures, but there's was a little extra on the monotone restriction and so on. Okay, so just a quick review of iterative deepening. Why do we want it? Because we want to have our cake of low space complexity along with completeness and optimality. And the key idea here is to recompute elements of the frontier instead of saving them, right? And if you do that, then we'll change this complete not to complete yes and optimal yes if we use iterative deepening. And the way to think about depth-bounded search is I think I like this analogy, it's DFS on a leash. It's like a dog on a leash. It can only go so far before you yank its leash and bring it back, right? So with a depth-bound D, ignore any paths with a longer length. Do not allow it to go too far away. We backtrack. It's called failing unnaturally. It's not failing naturally would be getting to the leaves of the tree, finding that they're not goals, and then backing up and exploring other paths. That's a natural fail. An unnatural fail is just hitting the depth bound. There are indeed leaves or nodes beyond there, but you don't want to go there yet. You'll go there in later iterations. And the key point is there's only a finite number of paths with length less than or equal to d, so it always terminates. So what's the memory requirement at depth bound D? If m is the length of the optimal solution path, b is the branching factor. This should be off the top of your head. MB, thank you. Sorry, BD. It's the yeah. This D is the depth. It was MB when it was going down to the bottom, but we're not going to the leaves. M is where the leaves are, where the solutions are. The D is the depth bound. Okay? So my slides corrected me. So you progressively increase the depth bound until you find a solution or until you run out of time or memory or whatever your limit is. So this is just a nice graphic illustrating running the algorithms first with the depth is 1. So you expand this node here. Again, we're ordering the nodes, numbering them. You expand this node, but its neighbors are not added to the frontier because of the depth bound. Okay, same for that node. Depth 2, you go back down there. And just always cut off at the depth bound, just if you haven't found a solution yet. So this 8 turns out to be a solution. This node is expanded. So you generated this node on the previous pass with d equals 2, but you didn't expand it until d was equal to 3, till it was at the depth bound, not beyond it. Okay, so that's again critical to do it that way. So what's the space complexity? If you actually find a solution, then it's order BM, right? Green, yeah. Is it complete? It's guaranteed to find a solution if one exists, yes, because there's only a finite number of paths up to depth M where the solution is. So you can see how it's simulating simulating breadth first, right? By advancing the depth bound one at a time, it's doing a breadth first simulation. Is it optimal? Yes or no? Assuming our costs are 1. Yeah, because it's guaranteed to find the shortest one. As opposed to standard depth first search, which is not. And you can easily prove that by contradiction. I'm going through this quickly because it's really just review. I just represented the material. So what's the time complexity? We know what the space complexity is, linear in M and B. The solution is at depth M, the branching factor is B. The total number of paths generated, which is what governs the time complexity, is less than or equal to b to the m is the number of paths at depth M. You know, if the solution were way over on the right-hand side at depth M, then you might have b to the m paths. And you only expand them once. But you expand the paths at one level higher twice, and one level higher than that 3 times. Till right at the top, at the depth 1, you expand that m times. So that's where all the repetition is. But this term dominates this sum. So that, as we did with a little fancy algebra, here we just take the b to the m out of this sum. We get this sum, which is this. We just rewrite it as that because we want to have a number which is less than 1. B is greater than 1. And that sum there is less than or equal to the same sum going from 0 to infinity. We just added some positive terms, so it can only get bigger. And we know where there's an analytic solution. You could look that up in a table of analytic solutions to sums, or you can actually derive it using this idea down here, which is kind of cool, that I can only remember this one. I can never remember this sum. So just remember, for a geometric series, if you've got 1 plus r squared plus r cubed, where r is less than 1, that's going to converge. It will have a finite sum, and that finite sum is exactly 1 over 1 minus r. You can get that from the Taylor series expansion at r equals 0 of that thing, right? You remember that from calculus. So if we differentiate the left-hand side and the right-hand side by r, take the differential in, you get the derivative of r to the I is I times r to the I minus 1. The derivative of this is 1 over 1 minus r squared. So this has this closed form sum, which is really pretty. And so this number here, which looks big, is only b to the m times b over b minus 1 squared. And that's still only order b to the m if b is greater than 1. Right? This is a constant factor, like 6 or 10 or some small constant. So we can just drop it in the big O notation. So the time complexity of iterative deepening search is the same as depth first search as far as the big O is concerned. And in reality, it's only a few times larger. But it get all these optimality and completeness guarantees. Yeah?
Instead of recomputing, can we use caches and store the results?
Instead of recomputing. No, because the whole idea is you want linear space. And I mean, you could try it, but I'm guessing that this simpler algorithm will even be faster than any caching scheme. I mean, you're essentially going to be reproducing breadth first search if you do that. So you're going to get exponentially exploding space, and we're trying to stay with linear space. Okay? And the thing is, with exponential space, you're guaranteed to have exponential time. Whereas if you've got linear space, and on real problems, you'll find it's much less than exponential time, typically. So the code is given. We give a pseudo-algorithm in the book, in this section. It redoes a lot of work, but in fact, it's not much more than what depth first search does, because it's the first levels that get done most often, and they are the cheapest levels to look at. Okay, so time complexity is the same as single DFS, just like the last blah, blah, blah. It's the last level that dominates the search complexity. So space complexities, OBM, optimal complete. The other algorithm we looked at was IDA star. It's actually really a misnomer to call it IDA star, because it's not like A star. It doesn't even maintain a frontier. It's really simple. It's beautifully simple. But it has the power of A star, in fact, more powerful than A star in some ways. So the idea is simply just use iterative deepening depth first search, but we now have a quote depth bound, in scare quotes. The depth bound will be the F values, and we'll bump them up as we need to find more and more nodes. Okay? So the depth bound is measured in terms of the F value. So it's an F value bounded DFS, really. DFS on an F value leash instead of a depth leash. So that's why I'm saying it's a bit of a misnomer. The only thing in common with A star is it still uses the F value, the cost so far. F of P is the cost of path so far plus the estimate so far. It doesn't expand the path to the lowest F value. It's just doing depth first search. Okay, left to right depth first search, but we have a failure bound at some F value. You start out by setting it at the F value of the start node. okay? And then it expands that node to get its successors. And it doesn't then go on to expand the successors yet. It says which of those successors has the least f value. That's my new f bound. I will go to that f bound, which will then go to that node and expand its successors. And I'd say which of those nodes, or the other nodes I left behind, has the least f value. That's my new f value. So you just, instead of increasing it, the depth bound in integer values, you increase it in delta f's that just are enough to capture the next node. And you don't know where that's going to be in the search tree, but it's always going down the optimal path. Okay? So it does. So it'll explore all nodes with f value less than or f min, which is the optimal one, and eventually it'll pick up the optimal one. So is it complete and optimal? Under the same conditions as A star, if h is admissible, all arc costs are not just greater than 0, but actually greater than epsilon, which is greater than 0. And there's a finite branching factor, it'll work. The time complexity is, of course, still exponential. We're still in the realm of NP hard problems. What's the space complexity? What is it? Linear. It's only one linear, well, this linear one here, right? Okay, so we've now added ADA star to our set of algorithms. So it is complete and optimal under the A star conditions, and it's linear space complexity, which gives it the potential for sub-exponential time, which is the key thing we're mostly interested in. So these are the learning goals for this class. They're quite similar to the learning goals for the last class, because a lot of this was reviews. I think I lost a few last time. So do the exercises. And this is the learning goals for the entire search module. Okay, you should be able to test yourself on all of these learning goals, every single one of them. Okay? Let's say the only thing we've got to do next is, in search, is look at depth first branch and bound. Very important algorithm, and then we're on to constraint satisfaction. So read ahead in chapter 4, and I'll see you on Friday.